Okay, so what I want to do for question 4, so there's kind of two approaches to question 4. If you thought question 4 was easy one way, you could probably try the other approach. This typo has been fixed. So basically what you want to do is you want to determine what m and n are, right? And the way you have of doing it is you get to add a y, and the y has to be less than 1, and it has to be rational and positive. And once you add it, Tom tells you the numerator of the sum. Yeah? Okay. Um, okay. So the one what you could do then is you could look at the numerator of the sum and then you pick another y, right? Add it again and then get another numerator and then try to find m in it. Yeah? Okay, so that's kind of like probably the most straightforward approach. A more challenging approach would be you pick your y's before you look at the numerator of the first one. So you pick both your fractions less than 1 before even looking at what Tom gave you. And see if you can solve it all in one go. That makes sense? Okay. Um, so I guess my approach will be the first one. Okay. And I think it's interesting because so this is another situation where we're trying to justify partial marks. Okay. Okay. So student gave the following solution. So you pick P and Q, coprime M and N. Okay. And then you add 1 on P and you add 1 on Q. Okay. And what you get is you get PM plus N on MP, and you get QM plus N on NQ, right? Okay, so if these numbers are prime, right, then these fractions are already simplified, okay? Because the N it cancels with the N, so if it cancels here, it has to cancel with either the P or something in the M, right? But we already know it has nothing to do with the M, and the P is defined to be co-prime, so it doesn't cancel with the N, right? And the P already cancels this side, so it has to cancel the N, but we said they're co-primes, so it doesn't cancel, yeah? So the numerator is PM plus N, and here the numerator is QM plus N, for the same reason, yeah? Okay. And now you have two equations in two unknowns, okay? So you can just solve them for M and N, okay? Is that a correct solution? So does that constitute a proof? So Min, Ben, Chen, Zahan, what do you think? Yes or no? Is that a solution? Or is that not a solution? Huh?
Feels right, but sounds a bit sketchy.
Yeah,
So it feels right. I presented it right, but in a sus way.
it's like it's true, but you almost think it's not because it's so, it
I have
seems
a,
so simple.
I have a feeling they neglected an edge case or something.
Okay. So you all have good instincts. Okay. So then I tell you that this is not a correct solution. Okay. So then the question is, can you tell me what's wrong with the solution? Okay. So I'll give you a little bit of time. The coprime means that it shares no common factors.
Oh, what if like maybe
The Q and P are prime numbers. Yeah, so the y that we picked is y is 1 on P and y is 1 on Q. Yeah? And they're both less than 1. Okay, I'll give you a little bit of time, not too much time. So where's the mistake in this proof? Okay. I'll give you another 2 minutes.
What's if N and P are the same?
N and P.
Yeah.
Oh, yes, I guess they said P and Q were co-prime to M and N. See?
Oh.
Hmm. So, so I have these two. So this is what they tell you, right? So you know like K and then you know L, right? Okay, and you can like say subtract them and you get P minus Q times M equals K minus L, right? And then M equals K minus L on P minus Q. And if you know M, you can find N. For example, N is equal to K minus P times K minus L and P minus Q. Yeah. So I mean, there's a small issue. P can't equal Q, right? But that's not going to be the thing that breaks this. Okay, you can just make the P and Q different. Okay. Okay, online, any last chance? You have anything you want to say? Last chance? Okay, so see, all of this stuff here is actually correct, yeah? So the trouble actually is with the definition. Okay? It's like, how can you define P and Q to be co-prime to M and N when you don't even know what M and N is? Yeah? That's what you're trying to find, right? So you don't know what they are. How do you know your P and Q? So it's basically what you're saying, right? Like, what if P is just happen to be not co-prime with M and N? You're not allowed to define that. Yeah. So if you make it a prime, then what happens is this step here, the prime could divide the n. So it might not give you this. It might give you Pm. It might give you m plus n on P, right? So the P might cancel. Does that make sense? And here you get m plus n on Q. Yeah? Okay. Okay, so this is actually my starting point for this problem. I didn't actually get a chance to solve it myself. I only saw a student's incorrect solution. Okay, so I had to point out the error, but I'm curious to see if it can be recovered into a solution. Okay, so now the question is, can you try to salvage this into a solution? Okay, so I'll give you 3 minutes to think about that. Okay, maybe a yes in the chat is that you understand what the issue is. Okay, we have one yes. Yeah, so basically if p goes into n, then this p can cancel and make it m plus n on p. Yeah? So you don't actually know what your equation is. Is it this thing equals k, or is it pm plus n equals k? You don't know. Okay? Okay. Okay, I'll give you 1 more minute. Okay, yeah, I guess it's not quite enough time, but at least you're kind of thinking in that direction. So, okay, so how did I try to fix it? Well, I noticed that first of all, um, you don't necessarily need both equations to solve for m and n, okay? Because there's this thing called the division algorithm, right? And if you do a division algorithm, then the remainder is unique, for example, okay? So if you can write it as quotient remainder, then you can get both m and n in one go, okay? So then I was like, okay, well, if I don't need both equations, then I don't need both p and q to be coprime, yeah? Okay. Um, can I just get one of them to be coprime? All right. So obviously I have no hope of getting the first one to be coprime because I have no idea what m and n are, right? But once I got the first one in, yeah, I have some information now, yeah? Maybe I can deduce from that roughly something about m and n, yeah? So for example, we can see if I do this, okay, that could give me m plus n on p, or it could give me pm plus n, right? But no matter which one it gives me, you see the answer is bigger than m, for example. You see? Whatever the answer is bigger than m, yeah? But it might not be bigger than n, okay? It might be the other one, right? Okay. But it's bigger than n over p, yeah? And I know exactly what n over p, I know exactly what p is, right? So basically what I'm saying is if I pick my q, now let's make a capital Q instead of lowercase q, okay? If I pick that bigger than whatever answer I get times by p, yeah, then q is going to be bigger than both m and n. That makes sense? And if a prime is bigger than m and n, then it's coprime to both m and n. right? Does that make sense? Okay. So at the moment, what do I have? So what does this look like now? So what do I do? So I take any p, okay? P is any prime, yeah? And then I do m on n plus 1 on p, yeah? And that's either equal to pm plus n if p does not divide n, or it's m plus n on p if p divides n, right? Okay. But whatever this is, okay, so this is like numerator. Whatever this is at least n over p, yeah? And it's at least m, right? So let's call the numerator n, okay? So if I times n by p, yeah, then pn is greater than or equal to n, and pn is greater than or equal to m, right? Okay. Actually, we know they're non-zero, right? So they're actually strictly greater than n, and strictly greater than m. Okay. So all we need is q is prime greater than pn, right? Okay. So then what do we have? Then we do the 1 on q thing. I'll do it in blue. And have q m over n plus 1 on q. Okay, now we know it's equal to qm. So this is the numerator. Yeah. We know it's equal to qm plus n now. Yeah. Does that make sense? Because the q is co-prime. Okay. But furthermore, we know that n is less than q, right? So that means this is the quotient and remainder and the divisor in the division algorithm when you divide by q, right? And the quotient and the remainder are unique, right? So then you can read off m and n, okay? Does that make sense? Can I have a yes in the chat if that makes sense? Okay, we got 3 yeses and a yes and a years. Okay. Okay, good. So I think at the beginning of your maths, it's okay if you just write down exactly how you solve it, okay? But when you get older, like you want to write something for someone else who can't solve it to understand the solution. You understand? So what are some issues with just saying this? So like let P be any prime, yeah? This is logically correct, yes? Let P be any prime. You get this. Let Q be a prime bigger than Pn. Okay. Okay. How do we know Q exists, by the way?
Because it's infinitely many.
Because there's infinitely many prime. Okay. Okay. So we're citing this lemma saying there's infinitely many primes, and we don't prove it. Okay. And then we have the 1 on P, and then we do all this, and then we get it. Yeah? Okay. But that's not how you might write it up. Okay. So what are 2 issues? Can anyone tell me? What are 2 issues that make this possibly a difficult thing for someone else to read? Or something that's not elegant? You know?
Probably not 4 words.
No, no. We're not talking like style.
Maybe there's too many variables.
Yeah, actually, that's a good one. So So one thing that I think people will have trouble with is the fact that P is any prime, right? That makes sense? Like obviously it's nice to let people know it doesn't matter what P is, okay? But you could remove the number of variables by actually fixing what P is. That makes sense? So if it could be any prime, why can't you just do the proof with 2, right? Kind of like let people down a bit easy, you know? Like you don't have to make them think as hard as you did to solve it. Does that make sense? Okay, that's a good one. What else? Yeah, so the issue is still with the infinitely many primes, okay? So it's not an issue logically, but it is an issue, I guess, of elegance, okay? So what happens is when someone who doesn't know why there's infinitely many primes reads this, they're gonna have trouble understanding it, okay? Um, Whereas obviously there's gonna be eventually things where you have to do that, right? But like the question is it avoidable, right? Kind of like the P, we can set P equals 2, that's avoidable, right? So is it avoidable? So this is called self-contained, okay? So is this solution self-contained? Well, it doesn't seem to be because we're citing that there's infinitely many primes, okay? And we're not giving a proof, so then it's kind of like a mystery hole in our argument. If the proof takes 10,000 pages, then our proof, even though it looks like it's 5 lines long, is secretly 10,000 pages and 5 lines long. You know what I'm saying? So, so the question is, can you remove the need to cite that there are infinitely many primes? Okay. So obviously these are issues you don't want to think about if like this is your first time in a tournament and you just don't even know how to solve questions and stuff. You just want to get it over with. But this is something you definitely can practice at home so that when you come down to it, like this is mostly preparation. It doesn't require too much ingenuity. Okay. But it's not nothing, so people kind of get a bit like, oh, I can't believe I have to do this. Okay, so your task in the next 10 minutes or less is to come up with a write-up of this solution, okay? And then we'll write it up together. So come up with a write-up. It has to solve those two issues, okay? Yeah, so I've actually got people trying to quote much crazier theorems than infinitely many primes, okay? Um, so, technically it's okay, and it's okay to quote things like Dirichlet's theorem, which is like there's not just infinitely many primes, there's infinitely many primes like A mod B, where A and B are coping. Okay. But then people like quoting like Mihalescu's theorem, which was like a conjecture until like not too long ago. So it's getting crazy. One day people will be quoting Fermat's last theorem in the Olympiad, but it's kind of getting out of control. So let's produce a nice self-contained proof. Okay. So how do we write this up?
I think I've got a way of solving of trying to prove that there are infinitely many primes.
Oh, nice. Yeah, I guess the proof of there being infinitely primes is similar to how you can avoid the theorem. Yeah. How do you prove those infinitely primes, Benjamin?
I guess here we can use two theorems that well actually one theorem and one lemma I think that Euclid proved. So one that every integer larger than one has a prime factor at some point.
Yeah.
And so result of this, if I remember correctly, is that if we consider a finite list of primes from P1 to PR and we consider a number that is larger than 1, it has a prime factor. It has a prime factor according to Euclid's first lemma.
Yeah.
But the thing is, this prime factor that has can't be in the set of finite primes that we considered since this number larger than 1 that we are taking has a remainder 1 when we divide it by each of these primes in that set. So a prime factor of this number is not actually on the list. And so
Yes.
prove that for every number, if we consider a finite number of prime factors, there will always be at least one prime factor that is not on that set.
Hmm. Does everyone understand that? So this was Euclid's original argument about why there were infinitely many primes. Yeah. So if there weren't infinitely many primes, and you only had finitely many, you could times them together and plus one, and that number has to be divisible by a prime factor. But it has a remainder one with all the primes on the list, so it can't be one of the ones that are already on your list. Okay. Yeah, and we can definitely use this idea to make our proof self-contained. So one thing I want to note is like this is not just like a purely academic exercise. Does that make sense? It's not just like, oh, we're doing it to make it look nice. Okay, it does have practical consequences as well. Okay, because what is this practical benefit of having a nice proof? Okay, it goes into what I'm keep saying is the quality of a mathematician. It's a certainty. Okay, a nice proof you can quickly see if you're right or wrong. Okay, so it's not about being right; it's about being certain you're right. Okay, and if you know it's wrong, it's actually beneficial because you can fix things, right? Yeah. So the other one wasn't very nice because the assumption was kind of hidden, right? And that's what was wrong with it. And if something's not self-contained, you don't know if the theorem is actually true or not because you might have stated it wrong, right? And if P could be something else, it makes you think of all these other things. And so um, it makes it harder to see if it's right or wrong. Okay, Benchen, you want to say something else?
So I think there was actually another proof by Euler that used a geometric series. I forgot what it was though.
Yeah, I think it was like harmonic. Wait, yeah, it was like a series proof by Euler. Yeah. Um, yeah. So, okay, let's apply this to our example. Okay. So the Euclid one is suffices for us. Actually, the Euler one will be interesting when we start learning things like Dirichlet's theorem. Okay, because we are trying to prove. So that's what allows us to maybe prove other kinds of primes are infinite as well. Okay, so the first problem we already solved. Okay, is basically um, we instead of using p equals 2, yeah, we instead of having p, we have p equals 2, yeah, yes, that's less than 1, be our first positive negative y1 fraction, okay, which returns um a numerator of n1. Yeah? Okay. Alright. Since so m on n plus 1 on 2 equals 2m plus n1 equals 2m plus n, or n1 equals m plus n on 2. Yeah? Makes sense so far, yeah? So 2m plus n, or n1 equals m plus n on 2. Yeah? Makes sense? Alright. In either case, 2n1 is greater than m, and 2n1 is greater than n. Right? Okay, so the 2 times n1 is greater than n, and it's greater than m. So now we want our q, right? So instead of just saying q is greater than 2n1, right? We can literally, and it's co-prime to m and n, right? We can, okay, so, actually, do we have a good way of doing this? So we can try to get something that's, let's see. There's a slight issue with what I'm going to do. So we can kind of do something in the proof of the Euclid's thing by timesing stuff together and adding 1. You know what I mean? Okay, so the issue here. What is the issue? Yeah, I guess the issue is we don't really know what m and n are still, right? So can we make a q more explicit without using the infinite primes? So we need q. So what was our proof before? We need q to be bigger than 2n1. Yeah. And we need q. So so we need q to be co-prime. Do we need q to be co-prime to m and n? It seems like we only need q to be co-prime to n, right? Yeah. Okay, but we still don't know what n is. Okay.
Where can add 1?
Huh? Square root and add 1?
Wait, if you just add 1, doesn't that automatically make it so right?
Yeah, but we don't know what n is to add 1. Like, we are going to add 1 to stuff we know. So we can add 1 to n1. We can add 1 to 2n1. So actually, can you see that n1, is it obvious that n1 is co-prime to n? So n1 is co-prime to n. You know? It's actually co-prime to m as well. Is that obvious? Okay, because if it has a common factor, see if it has a common factor with n, right? Then whatever common factor it has to also be a common factor of m, right? But m has no common factor with n, right? So n1 actually is co-prime to n already, you know? So, um, okay, so what can you do then, yeah? So how can you make your Q? So you can't just do like n1 plus 1, right? Because then like it's it could now be got factors with n now, right? Like n1 didn't, but n1 plus 1 might, right? And m might be m minus 1 or something, you know?
Isn't square one?
All right, so he's ahead of me. Okay, so we could also try 2n1, right? Okay, but the problem with 2n1 is the 2 could now have a factor in common with um, n, right? So if you let q be 2n1, it might have a common factor with n, right? Okay, but Ryan had this great idea. We could do n1 squared, right? Yeah? So n1 squared is actually bigger than 2n1, right? Okay. Q is greater than n, and Q is greater than m, as well as Q is co-prime to n, right? Yes? Okay. Y2 equals 1 on Q, be the second positive fraction, and we get the second numerator, and 2 equals, that's mq plus n, right? Yeah? So now q is not a prime anymore, yeah? But it serves its purpose, you see? You now divide n2 by q and read m of as the quotient and n as the remainder. Yeah? Yeah, sometimes it's hard to convince people this is a better proof, right? But can you see at least it meets the criteria I set out? So you can check this completely now, okay? Without any trust. And you don't have to worry about P being any prime, you can just look at 2, right? So this is put that maybe in the server. Okay, you guys have any questions about that? Does that make sense? I got like a yes in the chat. You understand? Alright, excellent. Yeah, and so if you don't understand what I mean by read off as a quotient and remainder, it's like you just literally divide it by q, round it to the nearest integer, like the lower integer. That's the m, right? And then the fraction part, you times it back by q, and that's the n, yeah? Okay.